Hello everyone, welcome to Aspen Plus tutorial videos. In this week videos, we're gonna talk about, or we're gonna pick up what we left last time, which is on the topic of assigning utility and monitor CO2 emission. For this week videos, I'm gonna focus more on the carbon dioxide tracking or carbon tracking, if you will. So that's the part that we will review or discuss in this week videos. To be honest, this video I think will be quite quick, quite short, because there's not much to talk about, to be honest, because carbon tracking or carbon dioxide tracking, if you will, is basically a new feature of Aspen Plus, but they are located under the utility tab or utility input box. So when you choose your own utility, you will see that there will be a carbon tracking option, and there is the place where you will input the relevant information that are associated with carbon dioxide emission or carbon dioxide release, especially when you are using a utility, when you are using utility for your plant. And for this week, if you remember last time, the process that we simulate, okay, to just for demonstration purposes, was the separation of n-heptane from toluene using extractive distillation, in which the NMP was the solvent. So yeah, let's move on. So if you remember, I did talk about utility. What is it all about? What is the type of utility that are often found in the chemical plant or in the refinery, and their associated costs, as well as their recommended temperature. So as I said, in different books, you will see there's a different values, even in Aspen, they have different values as well. So it's up to you, I guess, to decide what is the condition of your utility. I'm not going to talk details or talk details about this about utility, because I already mentioned this in my past video. So if you want to refer to my past video, please go to my channels and then find the videos. I think videos part 1, if I'm not mistaken. So moving on, this is just a continuation of different types of utility that you often found. For example, cooling water, fire heater, or hot oil, or HTF here means heat transfer fluid. I'm not going to go into details here. So yeah, if you remember last time, our objective for part 1 was to separate NMP from the, to separate n-heptane from toluene using NMP as a solvent, and we have successfully separate them, okay, using the this process where we have a 2 distillation column, where the first one is you will get n-heptane on the distillate section of your column, and then the bottom part will enter the second column, in which the toluene will be recovered on the distillate part of your second distillation column. And after that, if you remember, we did assign a utility for our condenser and reboiler and monitor its usage, and if you, as well as it's what's the cost, okay, to use the utility. In this case, we was able to obtain the cooling water usage around 200 ton per hour, and this is the amount of this is the cost for cooling water, which is $1.7 per hour. And if you think that this for this amount, for this 200 ton of cooling water is and the cost of it was only it's about $2, it kind of makes sense, because even in Malaysia, right, the 1 cubic meter of water, okay, I don't really remember what's the tariff, maybe 0.15 ringgit. So 1 cubic meter is around 1 ton. So 200 ton. So you just need to multiply 0.15 multiply by 200. You will probably get around, I don't know, maybe 5 ringgit. I have no idea. But what I'm trying to say here is cooling water in general is quite cheap. Now, if you see the one highlighted on the red one, we have the cost of using high pressure steam. in the reboiler section, because we need high pressure steam to reboil, okay, the bottom product, to evaporate them, okay, for them to undergo a phase change. Not going to go into details, but what I'm trying to say here is we were able to obtain the usage, okay, the rate or the amount, okay, required for high pressure steam for column number 1 as well as column number 2. Actually, when I did the simulation yesterday, this could be a wrong number, by the way. These are correct, the costs are correct, but the amount probably is not right. I think this is around 10,000, by the way. This is close, 6,500 or 6,400, but this is a typo, if I'm not mistaken. It should be 10,000. Okay, so that's all I want to mention. And then moving on to before we move on to part 2, right? I just want to talk about a little. I just want to talk a little bit about CO2 tracking option. So if you activate this CO2 tracking option, or if you decide to put information, okay, to on the CO2 tracking option input box, it is quite useful features for you to evaluate the process sustainability, so that you can monitor how much CO2, okay, being emitted to the atmospheres because when running your plant. So it's very good for you to find what is the carbon footprint as well as water footprint for your process. Especially all of the companies are right now are very put quite a high emphasis on the sustainability part of their plant. So yeah, when you evaluate the CO2 emission, okay, so you can kind of like kind of monitor, I guess, what's the global warming potential for your plant, because as we all know, CO2 and other gases, there are 5 actually, the major greenhouse gases, which I will discuss later on, that can trap heat and then contributes to the global warming. Now, when I say monitor CO2 emission in Aspen Plus, it means that emission that are associated with running your plant only. Anything outside of your plant, such as like the carbon dioxide emission due to transporting your raw materials, transporting of your maybe electricity, for example, this one is not part of the CO2 emission in Aspen Plus. It is only, they only monitor the direct total emission to produce utility, that's number 1, as well as from the process stream itself. So if you see here, this is the if you activate or if you use the utility option in Aspen Plus, you will see something like this. And then this is under carbon tracking or CO2 tracking, if you will, where you will have a CO2 emission factor data source, and then here you will have a United States EPA, Environmental Protection Agency rule. So this is the database that they use for a wide variety of fuel, okay, that they compile and then put it in Aspen for you to use, for example, you can have a coal. Even coal, in this database, they have a lot of different coals. You can have naphtha, natural gas, and things like that as a fuel to generate or to produce your own utility. There are 4 options. I think you have a user-defined option where you have to specify your own. And then in here, the default one is US EPA database, and then you also have a European Union database. So it's up to you whether you want to use your own data or use the database of Aspen Plus. Ultimate fuel source here is as I said, it is the fuel that you use to generate your utility. So the default one was a natural gas. CO2 emission factors here means for every calorie of energy that you produce using natural gas, okay, what is the amount of carbon dioxide in kilogram that you produce. Okay. Now, CO2 energy source efficiency factors. This can be quite tricky, by the way. So how it calculates is like this. The default values is 85%. So let's say when you simulate a distillation column, you will get a utility duty. Okay. Now that utility duty will be supplied by your utility. Let me rephrase one more time, or let me explain one more time. Let's say, for example, when you simulate a distillation column, you will get a reboiler duty, for example, and normally this reboiler duty will be supplied, okay, by the high pressure steam or whatever utility that you have. So the total amount will be in kilojoule, kilocal, or what have you, right? And then how can we relate the steam duty to the fuel usage? Now, if you specify 0.85, meaning that fuel duty, utility duty is equal to fuel duty divided by 0.85, because in most process you cannot have like 100% efficiency, I'll say boiler, for example. So there's always so you need, normally the fuel duty that you use, okay, for example, for natural gas will always, in this case, let's say I have like 100 kilojoule of fuel, okay, and then if you specify 0.85, meaning that 85% of the entire fuel duty will be used to generate the high pressure steam. And then when you know what is the fuel duty, and then you know what is the total energy of your fuel, okay, combustion energy from your fuel, like say for example from diesel, you can get the fuel requirement, and then assuming that the diesel, okay, all of the carbon atom from your diesel is converted to carbon dioxide, then you will get a CO2 emission. Actually, there is no standard when it comes to giving this to provide this number. Is purely heuristic, so it may or may not be accurate to your plan. So you have to be a good engineer and decide, or maybe discuss with your superiors and decide what is the best numbers for your plan. Okay, moving on. So there are a few important information for you to remember, by the way. As I said, for CO2 tracking option, all carbon, elemental carbon in your diesel, or if your naphtha or of your coal, will be converted into carbon dioxide. So basically it's 100% conversion of carbon to carbon dioxide. 85%, as I mentioned just now, 85% of fuel energy is converted to steam energy. Now you might be asking me, okay, by the way, the remainder of energy is basically energy loss to surrounding, inefficient, maybe mechanical efficiency, okay, maybe heat transfer is not highly efficient, I guess. Other kind of things. So what I'm trying to say here, 85% of fuel energy will be converted into steam energy. Now, if you think why 0.85 or 85%, there are a lot of, there are a lot of ways for you to find there are a lot of ways for you to know how they get these numbers. Number one, if you go to this boiler, okay, this is a boiler handbook, by the way. If you see here, all of this refers to the boiler efficiencies, and all of it, and most of the time, they are around 80 to maybe close to 88%. So this is a boiler handbook, by the way. So I think that's where they get the values. And then the second references here, if you see by Chavez Velasco here, is published, I think, this year. They use boiler efficiency 85%, and then you can you see here they refer to 29, and then I check what is the reference 29, and they refer to this boiler handbook. So this is where you get your boiler efficiency. So this CO2 energy source efficiency factors, you can simply say that it is how efficient is your boiler, and the normal boiler is around 85%. Okay, moving on. So for our design problem, it's very simple. This is a hypothesis. This is a hypothetical process, I guess. No, it's not hypothetical. It's that I just design it this way. Okay, just bear with me. So I have the same process. And then I still use the high pressure steam, but in this case, right? Let's say, for example, I use a traditional pulverized coal as my fuel, and then I also have the CO2 capture technology that are able to capture 90% of the CO2, right? And actually, this number is not a made-up number. So it is, if you Google, right, if you refer to a blog or if you refer even to Wikipedia, this SAS power, okay, is an actual power plant, by the way, in Canada. Okay, this power plant utilize CO2 capture technology when they are generating their electricity, and of course, when they capture CO2, they was able to obtain around 90% of the CO2 produced during the combustion process. And obviously, when you capture CO2, the overall cost of utility generation will increase because you have extra step to capture CO2. In this case, I'm just going to give a random number. Maybe in this case, I'm just going to assume the cost will be 15% higher. Okay, this is just an example. So an analogy that I can give you is like this. Okay, you know, like a vegetable, right? If you go to a groceries and you buy a vegetable, okay, normally the normal vegetable that people produce commercially is quite cheap, and then let's say if you want to like a organic, okay, pure organic vegetable, normally they are more expensive because, you know, they have a specific way of growing their vegetables. Same goes with this one. Okay, in this case it is more expensive because they have their own process to produce electricity, in which they have an extra step to capture CO2. But because of that extra step, they have to increase the cost of their electricity, so that they have a you know, if they don't increase the utility or electricity cost, right, obviously they're not going to make any money. But never mind. Yeah, this is the images. I took these images from this website. You can go ahead and look. It is I think this blog is about carbon capture technology, if I'm not mistaken. So that's all for the introduction. I'm going to move on to my Aspen Plus. So if you see here, this is my simulation. Actually, I already got a result with, I got a result here, simulation converge, so no issues. And in fact, this is a past simulation and I didn't do anything about it, except that I have utility high pressure steam for my reboiler. So if I have, if you remember, so how did I created this utility? High pressure steam, you have to refer back to my past video. So if I click the input, you will see that these are the steam, these are the prices, okay? These are the conditions. I already mentioned all of this in my past videos, so I'm not going to talk about this. And then if you refer here, there's a carbon tracking. And as I said, if you click here, you will see there's a user option. I have a European Union, okay, data source. And then you have, as I said, user defined data. Fuel source, you have a lot of different fuel source. You have wood, waste oil, petroleum coke, coal, biogas, asphalt. Even, I think if I'm not mistaken, they also use municipal solid waste. So there's a lot of research going on, and then they probably US EPA probably got data from all of this. Fuel source from research on using different kind of fuel source, and then put it here. And here I have a CO2 emission factors. Okay, if you use the US EPA, you cannot change this one, by the way. Okay, this CO2 emission factors. Okay, let's say for example I decided to use this one. to use this what is it called? These default values. And then what you need to do is just click run. Oh no, I cannot see the next button. I'll put my videos here. Oh yeah, by the way, I did run, so no need to do anything. So I have to go to under stream result. You can go to CO2 emission, and then you will see the net stream CO2e, meaning that CO2 equivalent. By the way, I will explain why it's called equivalent, and then I will get a utility CO2. Meaning that the CO2 generated to produce high pressure steam for my utility is around 1955. And the total is basically net stream plus utility stream. A net stream CO2 means that CO2 stream from your feed minus CO2 stream from your product. Since my NMP is just NMP, I don't have any CO2. And I don't have any chemical reaction to produce CO2, so that's fine. That's why it is a 0. So yeah, if you remember, in my process, I would like to use a coal as a pulverized coal as my fuel source. So I'm going to use coal here. So I'm just going to select coal. Actually, I have no idea which coal to use, but I'm just going to use industrial coal, by the way. So industrial coal, we produce around 4.145 kilogram of carbon dioxide per calorie of fuel produced. And then CO2 energy efficiency factors, I'm going to keep it constant because that's the boiler efficiencies. And then just click next, and then you should be able to get the result. This is before carbon capture, by the way, because if you remember, my carbon capture technology able to obtain around 90, able to capture around 90% of CO2. But let's see the result first. If I use a coal, I will get around 3464 and then 3464 kilogram per hour of CO2 for utility. Now, let's say I decided to implement the carbon capture technology. Instead of doing this, because I cannot change the CO2 emission factors, what I need to do is I just gonna go to the user function, okay, user define option, select, and then here I will type 0.41449 times 10 to the minus 7 kilogram per calorie. This is basically a 10% of CO2 because the remainder 90% is already being captured. Now, if you remember, if I the company, okay, because of this carbon capture technology, the cost of the electricity rises by 15%. So to reflect that, what I'm gonna do is I'm gonna change this energy price. So 15% higher than 2.5 is around 2.875. So there's the values, and then click next, and then hit OK. And I can go back and then go check for CO2 emission, and then you will see, if you remember previously, you get 3464, which is 3,464. And in this case, after carbon capture technology, you will get around 346 kilogram of CO2 emission. Okay, that's pretty much it. When it comes to utility CO2. Next, I'm going to talk about net stream CO2, which is CO2 coming from your feed stream, as well as minus product stream, which is coming from your stream. If your stream has CO2, then you will have a CO2 here. So to do a quick demo, what I'm going to do is I'm going to go to properties. I'm going to add CO2. Just to demonstrate you, okay, CO2. I'm gonna also add a methane, CH4. I'm gonna also add NO2, which is nitrous oxide, okay. And then I'm gonna hit next. Just run the simulation. Okay, available, and then I go to my process flow sheet. Let's see. Okay, let's say for example, I have another process in which let's see, view. What happened to my videos? I don't know why. Maybe I put here, or I put here. I go to view. Yes, view. Okay, view, model palette. I choose, let's say for example, I choose, this is a hypothetical process. I have a mixer here. Okay, maybe I put something here, and then I put something here. So for this one, I'm just gonna assume 100 degrees Celsius, 1 bar, and then I have mass flow of CO2, 1 kilogram per hour. Okay, so if you see, if I hit next, I'm just gonna run the simulation. Okay, so if you see, if you go to your simulation result and then go to CO2 emission, you would see that I have carbon 1 kilogram per hour in my stream. And then here, I also have 1 kilogram of carbon as my output. So the net will be a 0, by the way. I'm going to close this one so that you can see clearly. So because 1 minus 1 is 0, that's why you have a net stream CO2. So in terms of process, you're not producing, you're not reducing CO2 emission, CO2 at all. Now next, I'm going to show you what happened if I choose 1 kilogram of methane. If I hit run, okay, and then I go back to the result, you would see that it is 25 times. So in this case, methane, if you all know, every 1 kilo of methane is 25 or 24 times more potent, I would say, in capturing this thermal energy or radiant energy from the sun, which is the reason why it is called CO2 equivalent. It's kind of like 1 kilogram of CO2, how potent they are. Okay, like 1 kilogram of CO2 of methane is equal to 25 kilogram of CO2. That's why it's called CO2 equivalent. Okay, next, one last thing that I'm going to show. For example, what if I put 1 kilogram of nitrous oxide as opposed to methane? So if I click next, and then do the same, you would see it is 298%, and 298 times more potent than 1 kilogram of CO2. So yeah, I think that's pretty much it in terms of the simulation. I'm gonna wrap up everything by showing you a few of my slides as well as the result. So let's go back to our slides. So if you see here, this slide is very important for you to understand the net stream CO2 emission in Aspen Plus, because different component, okay, that you produce or that you use have a different CO2 equivalent. And if you remember, or if you Google quick search or journal reading, you will see that there are 5 major greenhouse gases. The first one is water vapor. The second one is carbon dioxide. The third one is methane. The fourth one is nitrous oxide. The fifth one is the fluorinated gas. Now, if you remember, 1 kilo in Aspen Plus, they use 1 kilogram of methane is equal to 25. So meaning that it is 25 times more potent. And if you see here, and it is, you can see that how it relate. Okay, these are the global warming potential. And then if you remember, 1 kilogram of nitrous oxide is around 298%. And if you see these figures, it is close to 300. And then of course, if you have a fluorinated gas, it can go up to 10,000 times more potent than CO2. But I have no idea what is the gases, so I'm not going to do any demo on that. And then this is just a breakdown on what are the amount, okay, the fraction, I guess, of from the total greenhouse gases emission from these 5 category of gases. Yeah, the images was taken from this website. You can go ahead and look. Now, if you all, when talking about global warming, we all know that CO2 is and methane is one of the contributor for global warming, and we all know that all molecules vibrate, and then their vibration normally vibration energy is not really that high, by the way, is as compared to energy coming from the nucleus part of your atoms. So when we talk about vibration, okay, all molecule vibrates, by the way. That's why we can use FTIR, okay, to identify the functional group, or what's the element or functional group from your materials. Because okay, if they because it just so happened that CO2, they vibrate in such a way that they vibrate, and their vibration energy sometimes can be represented by the wavelength, okay, of the radiant energy from the sun, okay. So if they match, they will absorb and then re-emit it back, and which is the reason why, okay, CO2 can technically trap, they can absorb and then release the CO2, causing the global warming, causing the Earth average temperature going up, so become hotter, so we cannot live comfortably. That's the reason why. By the way, I took this one from Wikipedia, so you can go ahead and look. Okay, one final thing that I want to discuss here is, if you remember, on the part 1, we were able to simulate the process, and these are the process. The column highlighted in the red, in the yellow one is the one from the textbook. So I was able to obtain the same values. So our simulation checks out. And then we also assigned a utility usage, and I was able to obtain the utility for cooling water and high pressure steam. This is 10,000, by the way, not 1,000. There's a typo, as well as, and finally, I was able to obtain what is the cost, okay, of utility usage. And after that, I was able to monitor or do some kind of a carbon dioxide tracking for my plant for generating the utility. And because my stream does not contain any of the greenhouse gases, so my net stream is 0. And this is a physical processes, and I don't do any chemical processes in which I produce CO2, meaning that I don't have a net CO2 production. That's why my net stream CO2 is also 0. Utility I do have, and the total CO2 emission equivalent is basically net stream plus utility stream, which is 346.398. So yeah, that would be all for me. If you like the videos, give it a thumbs up, or if you have something to discuss or to comment, please write down on the comment section, and I will see you guys in my next video. Okay, bye-bye.